Yeah, good afternoon. My name is Sandro Tacchella. I'm an assistant professor at the Department of Physics, the Cavendish Laboratory. And it's a great honor and pleasure to be here today and talk to you about the frontier of early galaxy formation. And this frontier, of course, has been moving very rapidly thanks to JWST, and I'm very excited to be here and present to you some of the newest result, and then also move on to some of the newer instruments that we are thinking about for the future. So again, I want to take you basically back in time, studying some of the earliest structures, luminous structures that we can observe in the early universe. And of course, observers have been doing this for many decades already. By looking at objects that are further and further away, we can look further and further back in time and basically try to reconstruct how the galaxy population looked back in time and evolved through cosmic time. However, I want to emphasize that, of course, we cannot really observe how an individual galaxy evolves, right? We only see the galaxy population at each epoch, and then we have to make kind of educated guess of actually how to connect the dots through cosmic time. There are a few exceptions. We heard about the archaeological approaches. For example, for the Milky Way, we can really do very careful look-back studies. But generally, when we think about galaxy populations, we have to be very careful with understanding how their physical growth actually takes place through cosmic time. So one of the most fundamental observables is, of course, the amount of star formation in the universe. This is showing you the cosmic star formation rate density as a function of look-back time up here and redshift here. And you can see that the cosmic star formation rate density in a co-moving volume basically is peaking around the redshift of 2. So this is basically a key epoch of galaxy formation where most of the stars in the universe formed, and then has been basically decreasing since then and also been ramping up at earlier cosmic times. So if you want to understand the shape of this, we can actually build up very, very simple models, even simpler than gulf form and semi-analytical models. We can actually just build up empirical models that we heard from Lisa Wechsler earlier this morning, where we basically just try to relate the star formation rate in a given dark matter halo to the accretion rate. And so to first order, we can then write this equation here, where we say, okay, we have lambda CDM, we have structure formation, so dark matter halos are growing with cosmic time. And the amount of star formation in a given dark matter halo at a given redshift is just some star formation efficiency times the baryon accretion rate. And in this simple model, we just assume that the baryon accretion rate is directly proportional to the dark matter accretion rate. So we just multiply the dark matter accretion rate with the baryon fraction, and we make this very strong assumption where we say that the star formation efficiency is constant and only depends on halo mass. At high redshifts, we are used to work with the UV luminosity function, so we can calibrate this model, for example, with the UV luminosity function redshift 4, where all the observers agree. And you can see that, you kind of get this typical curve that you have also seen from the stellar to halo mass relation in the local universe, where you see that the star formation efficiency needs to be suppressed in lower mass halos, peaks around 10 to the 11, 10 to the 12, and then decrease again at higher halo masses. Again, this model is so simple that there is basically no physical prescription for this, but of course you can write more complicated models down and make arguments for stellar feedback at low masses and black hole feedback regulating the star formation in high mass halos. So again, this is what we would assume is kind of a constant star formation efficiency model where there is no redshift evolution of the star formation efficiency. How well is such a model doing? So this is pre-JWST data. You can see here again the cosmic star formation rate density. This is redshift. We calibrate the model at redshift 4, so we are fitting that data point perfectly. And this model then basically very naturally reproduces the evolution of the cosmic star formation rate density to earlier times. You can see basically there's a 2 to 3 order of magnitude decrease in the cosmic star formation rate density out to redshift of 10. And this is mostly just because you're building up dark matter halos. And in some more detail, you can of course look at the star formation efficiency and now convolve this with the halo mass function that I'm overplotting here. And you can see that really from redshift 10 to redshift 4, you see how the halo mass function moves into this regime of having galaxies that are able to form stars very efficiently. So there are of course other models, and you can see that all the models basically agree kind of at lower redshift, but then there's large diversity because there's no data above redshift 10. And so the question is really, does the star formation efficiency, for example, evolve when we go to higher redshifts? And so with Hubble, you can see basically that we have been able to trace the rest frame optical up to about redshift 3. And beyond that, we mostly relied on the rest frame UV. And you can see that the data points were much sparser. And then, of course, let's build a $10 billion telescope and push this further back in time. So what you can see here is now that we are basically able to probe with the James Webb Space Telescope the red spectrum optical up to about redshift of 9. And then again above this, we are mostly relying on the rest UV with some exceptions thanks to the mid-infrared instrument MIRI. Now, what are the key questions? And I think they are very similar to what we tried to answer from redshift 0 to redshift 3, but actually pushing really the frontier now to earlier cosmic times, in particular the cosmic dawn epoch. So I think the key questions today are like, when did the very first black holes and galaxies and stars actually started to form, and how did they then evolve to build up the mature galaxy population that we can already see in place at cosmic noon? How do these objects actually reionize the universe? How do these objects chemically enrich? And then also build up the structure in the galaxies, right? How do bulge and disk components in galaxies form? And then also build the very first quiescent galaxies that we now see in place around redshifts 3 or 4. Now, I don't have time to really review all the great surveys that have been done. What I want to highlight here is that just there have been in the first 2 cycles of JWST a wide range of different surveys that really complement each other. So we have surveys that are really targeting large fields with a few filters, rather shallow, but then also some very deep pointings with several filters. And what I'm talking today about is mostly about the JADES survey. This survey stands for JWST Advanced Deep Extragalactic Survey and is a GTO program. So the strength of this survey is really to basically put together a synergy between photometry, the NIRCam science team, and spectroscopy, the NIRSpec science team. And we had several data releases, and Andy was highlighting the data release from the NIRSpec side 2 days ago. And I think here in Cambridge, I think the unique thing that we have is we have this strong leadership both in spectroscopy through Roberto Maulino and the imaging side from myself. And so we can really push basically with JADES the frontier, combining and really living this synergy between photometry, finding these interesting systems, and then with spectroscopy characterizing them in more detail. So I just want to show you basically how beautiful the data is. Okay, I have been leading large fraction of the data reduction actually. So we have been worrying a lot about scatter light effects. They have very scary names like wisps, claws, dragon breaths. And after we have removed all these features, and now we are really rewarded with these beautiful images. And I just want to dive into here, as it's showing you an image at 1, 2, and 4 micron. So we're zooming in a smaller region. This scale shows you 3 arc seconds. And again, it doesn't come to full, you should download the real image and you can scroll around in the real image online. But what it is highlighted just that you can see a diversity of galaxies, a wide range of different colors, shapes, and it's actually getting very difficult to think about how we should do the deblending because sources are not anymore that well defined. Is this, for example, one system, or should we count this as 2 systems? So there's a lot of interesting challenges also on the photometric side. Now, the key thing of JADES and of JWST in general is actually the spectroscopy, because that's really a major leap forward. And now we are able to do spectroscopy in space, directly in the prism mode, everything basically from below 1 micron up to 5 micron in one shot. So you can really get a lot of the emission lines that you want to learn about for example, studying metallicities. But then you also can use the grating modes, medium and high resolution gratings, and you can start resolving the line widths and shapes, which traces, for example, outflows or blotted line regions of HENs. So again, the frontier of JWST is moving very, very quickly, and there are about 4 papers in galaxy evolution on JWST every day. So I'm trying to give you here a very rough overview, highlighting in particular student works. And I focus on those 4 main topics, so first light, black hole growth, star formation, and morphology. So think about first light. You can see here basically the redshift, the spectroscopic redshift of the most distant object known. So in the before 60s, when a lot of people were lazy, it was just like technology, of course, that was still in development. And you can really see this ramp up. Of course, IOE had a key leadership there as well. And now with JWST, we really pushed basically beyond redshift 10. So looking at this a little bit more in detail, here I show you the UV magnitude. These are bright objects, these are faint objects. These are some of the photometric samples we are currently having, and all these colored points are the spectroscopically confirmed galaxies that we have now above redshift 9. This is incomplete down here, but the key thing is that we have over 7 galaxies now spectroscopically confirmed above redshift 12. Now, when we look at photometric samples, and there have been many different studies in this, I think the key thing there was that the bright end of the UV luminosity function evolves nearly not. It's remarkably constant. And the key there is, and again, we can do some comparison with models. I just want to highlight here, so this is showing you the observational data point that is now basically new with JWST. And so this constant star formation efficiency model that I highlighted to you before is basically down here. And so this is basically a factor of 2 to 4, where we have basically an overabundance of UV bright galaxy at high redshifts. So what are the challenges? Well, there are still challenges when it comes to data. For example, you can give the same data to different groups of observers, and they come up with different samples. So I think these are all candidates, so one has to keep this in mind. And the second thing is, of course, how do we actually compare the models to the observations, and something that I'm very interested in, but have only very little time to talk about. So how can we explain these UV bright galaxies around redshift 9 to 12? And so here basically building on Carlos' talk as well. So of course we can think about changing cosmology, but I think again there is always this strong degeneracy with baronic physics, and typically I prefer to actually think about the baronic physics before changing cosmology itself. On the baronic side, there have been many different scenarios being put forward. So for example, we can really just increase the star formation efficiency in halos. The motivation there is, for example, that you are in a low metallicity regime, which can increase the star formation efficiency. You can decrease the dust attenuation towards high redshift, something that Carlos mentioned. You can increase actually the scatter between halos and the UV. So again, the the halo mass function is very steep at high redshift. And so when you scatter things from the low mass end basically up, you can do this very efficiently with just a little bit of scatter. And so you can have low mass systems that actually dominate the bright end of the UV luminosity function. You can, of course, vary the initial mass function, therefore basically increase the UV output per baryon, or you can introduce non-stellar sources such as HEN. And so I want to discuss these ideas a bit more in the concept of the spectroscopically confirmed galaxies that we have. And I go here quite quickly, but we have these 4 galaxies that were the first ones that we discovered that were above redshift 11 and spectroscopically confirmed with JWST. This is showing the spectra that also Andy was highlighting 2 days ago. And again, once you have these distances basically confirmed, you can start thinking about how do you actually interpret the UV emission that you see in these galaxies. And so for this, we have been, over the years, in particular Ben Johnson, developing Prospector, which is a fully Bayesian SED modeling code. And we heard from Jane yesterday a very nice introduction of what are all the assumptions that go into this SED modeling from IMF, isochron stellar libraries that go into the simple stellar populations. And then we have to add a star formation history, a metallicity enrichment history, dust attenuation, as well as dust emission, and nebular emission as well. And I think Prospector does this very well, is very flexible, and because it's fully Bayesian, you can really assess the degeneracies between these different model ingredients, and also learn, for example, how much information is there actually in the data, where is the constraining power. And so when we do this, what we find for these systems now, fixing the redshift to the spectroscopically confirmed redshifts, is stellar masses of those galaxies to be of the order about 10 to the 8, 10 to the 9, and their star formation rates are about 1 to 2 solar masses per year. And you might say, well, 1 to 2 solar masses per year is like the Milky Way, is not like that interesting, right? But because the mass is so low, this implies actually a very, very quick doubling timescale, right? So you're doubling the mass basically every few tens of million years because of star formation. And together with the very compact sizes, you see that the star formation at surface density is actually extremely high, of up to about 200 solar masses per kiloparsec squared. Now, moving on, we have, I think it was this week, where this paper has been now accepted in Nature, where we basically put forward the discovery of this redshift 14 galaxy as part of the JADES and the JADES field survey. So pushing the redshift frontier to 14 was challenging, in particular in the first 2 years, because the filter sets that have been used with JWST were mostly these wideband filters, and there is a very strong degeneracy that was highlighted by Rohan Naidu, that these redshift 16 galaxies can also be just dusty starburst galaxies at a redshift of 5. And in order to address this problem, we introduced this medium band survey, which basically is just a signal pointing, but goes basically very deep. So we're talking of like 50 hours of integration for individual medium bands to basically sample the SED of these galaxies in much better detail. And this galaxy up here, that looks actually extremely bright, has been around for us, for actually the first 2 years already. But we were very suspicious that this is a redshift 14 galaxy because it's so absurdly bright. But with the medium bands, we started to be confident this is indeed a redshift 14 dropout. And we were able to then follow it up with spectroscopy, just to show you this system here. And this is the spectrum here. So you can see now that we get the slit basically nice aligned on this object, and you can nicely see the break, the Lyman break, and therefore, the redshift has been confirmed to be redshift 14.3. And you might say, well, but isn't this, part of this galaxy that is here in the foreground? And we also put a slit there, and you can see that the SEDs are very, very different. And if you would want to mistake this as a Balmer break, you have to basically move in redshift quite a bit. And the interesting part of this system is that it's very bright, but it's also very extended. It's of the order of about 200 parsec in size. And so again, here we don't think that the AGN is powering the emission. It's probably pure star formation. And then let's move on to another very bright system, GNC11, that we heard about as well already in several talks. And again, Andy Bunker showed this very beautiful spectrum here, confirming it to be at a redshift of 10.6. And what I want to highlight here is that this galaxy seems not to be alone. We have actually many dropout candidates in a 5 megaparsec sphere basically around these systems. We have 9 other galaxies. And so this might be actually an early overdensity. And this is, again, not something that that's something that I think we would expect from simple lambda CDM. Now, I don't have too much time to talk about decomposing the light of this system, but we have been doing a lot of work on the imaging side to decompose the light into a point source and extended component, trying to understand what powers this emission. But I think it's really the spectroscopy, and in Roberto's paper, this is very nicely highlighted, that there is a P Cygni feature in the C4 line, the overall continuous spectral slope, and also the densities that are implied by permitted line all point towards that actually there's a broadline region of an HEN hosted in this system. And when you look at the magnesium line, you would infer a black hole mass of about 10 to the 6 solar masses. So this is actually a very interesting regime, because now you're basically starting to gap this bridge between different black hole seed form mechanisms and the quasars that we're observing at later times. So again, in GNC11, the point source actually dominates the UV emission. And so here we think that the HN is powering a large fraction of the UV output that we observe. And so in summary, I think we cannot rule out or rule in any of these scenarios. I think the redshift above 10 galaxy population is actually very diverse when it comes to sizes, to attenuations, to star formation rates, to HN activity, and also intensity of star formation, which of course is very exciting, because this means that probably all of these mechanisms play some role. Moving on to black hole growth. Again, GNC11 is of course a very nice first step, but we also try to do population analysis. So in JADES, we have been looking into broadline regions of HENs as identified by broadened lines under the Balmer emission and absence of broad lines under the oxygen 3 emission, and also using narrow line type 2 HENs, particularly focusing on ionization lines in the UV. And all of these basically show that we see a lot of activity in HENs around the redshifts of about 4 to 7. And these black holes are actually very massive. So when you look at here, the black hole mass, stellar mass relation, and this is work done by Ignace here, as a student at the Cavendish, you can see that these black holes typically lie above the local stellar to black hole mass relation. So these, for a given stellar mass, the black holes are basically overly massive and lie above this relation. And when you look at the accretion rates onto these black holes, they are consistent with being Eddington or even super Eddington. And so it seems that this black hole growth in the early universe is very efficient, and something that we're also exploring together with the Boras-Chakis group, where we try to understand how can you explain these black holes. So this one is GNC11. This is the one that Ignace has discovered in the data. And I think the key takeaway by varying different modeling ingredients for how black holes grow in numerical simulations is that there's a range of seed masses that actually can explain the black hole mass we observe at later epochs. But what a key thing or feature is for these observations to be explained by these numerical simulations is that you need to have at least part in super Eddington accretion. So moving on to star formation. So here I want to discuss again basically this early star formation we have in the early universe. So when we look at direct in situ observations above redshift 10, I already mentioned to you that maybe there is an increase in the star formation efficiency in early galaxies. You might say, well, okay, but these galaxies are faint. You have only a few galaxies, and you only probe the rest from UV, and there are a lot of uncertainties of how you convert the UV luminosity into a star formation rate. So you can also go the other way. You can do this indirect approach, where you say, well, let's go to redshift 3 to 9, where we have access to the rest frame optical, and we can basically do this look-back approach, the archaeological approach, and try to understand how much stellar mass it actually formed up to that epoch. And so we started to do this. So there are these overly massive galaxies that have been claimed very quickly in the first 2 months, basically, by Ivo Labbe. And there, I think, there have been actually many issues with this work, I think. To one degree, there were calibration issues early in the data. But several of these objects have now been confirmed to be AGN, wrong distances, and overall the stellar masses are very uncertain because there are many assumptions that go into this as well. So you might say, well, okay, star-forming galaxies might not be the right approach, so let's look at massive quiescent galaxies at redshift 3 to 4. And here, again, people have been finding these very strong 4,000 Balmer breaks, basically, and these imply, again, rather old ages. And basically, when you look at formation histories of these galaxies, again, the stellar mass has assembled in these quiescent galaxies basically above redshift 10, so you need to form a 10 to the 11 solar mass system at redshift 10 or before, and this is, of course, also challenging given the current constraints. And so we have been looking into this with an undergraduate student actually here, and what we show here is the spectrum from exactly this galaxy, and what you see over plotted are different models, starting the star formation history at redshift 10, 20, and infinity, and you should basically see that these lines basically all agree very well with each other. And it's just highlighting that basically it's very difficult to tell apart stellar populations of age differences between 1.3 and 1.6 gigayear, which of course is a huge, space in redshift. And so when we do this modeling now, and just changing, for example, instead of having this flat continuity prior, but having a prior that is rising with time, following lambda CDM, what we expect for dark matter halos accretion rates, you basically, not anymore form all the mass in this first spin between redshift 10 and 20, but something that increases from redshift 20 basically to redshift 7, and much more consistent with the direct observations of the star formation rate of the galaxies I've shown you before. There is, of course, also when you think about star formation, the variability, the stochasticity in the star formation that is very important. And of course, it's very easy to detect the galaxies that are increasing the star formation, right, that are bursting. The challenge is really finding these quiescent galaxies, and Tobias Loser, a PhD student here, has discovered this very interesting object that is actually quite low in mass, but has a very quiescent spectrum, still a UV upturn there, but you can clearly see the absorption features and a rather strong 4,000 angstrom break. And again, these galaxies, I think, are expected when you have bursty star formation, right? Galaxies go up in star formation, but they also have to come down. And this is something we have been exploring with simulations, with Tibor Dome. And we're calling these galaxies mini-quenching because these galaxies are probably not quiescent for the rest of the history, but just quenched for a few tens of millions of years. And indeed, this is something that then Callum Witten, a PhD student at the IOA, nicely showed that we have systems where you can see a 4,000 angstrom break, but you can also see emission lines on top, which indicate that you have indeed had a lot of star formation early. You have this low in star formation, and then you have an increase again. Okay, and in the last few minutes, I want to just talk about morphology very briefly. Again, at redshift 2, we made, over the last few years, with in particular Hubble, a lot of these, discoveries that these galaxies are actually very mature. So we see, very, mature bulges with star-forming disks at redshift of 2. And the question is, of course, how do such galaxies form? Now, with William Baker, we have been finding this very interesting system. Again, this system has several path spans with NIRCam, and you can see it's very compact. And this is, of course, the challenge when you want to do morphology at high redshifts. And so one of the things we have been developing is basically measuring Cersei profiles, multiple Cersei profiles, and fitting this to these images, but then not anymore working on the mosaics, but on individual exposures, because we want to really use the full dither information of the images. And so we wrote this code so that it can run on GPUs, and it seems to work very well. And so what we're doing here is basically decompose the light into a central component, an extended component, and also we can fit the clump. And so we can then measure gradients in stellar mass, star formation rate, as shown here. And you can see that the stellar mass density is really dominated by the core, whereas the disk is dominating the overall star formation. And so we find, for example, in these systems, very strong gradients in the specific star formation rate, indicating that although these galaxies are very compact, only about 100, 200 parsecs, they grow very rapidly. They have a lot of star formation in the outskirts, given the stellar mass out there. And if you put this now in context of massive ellipticals, which sounds like crazy, right? Because this system is only about 10 to the 8, 10 to the 9, so you have to think about the mass increase by a factor of 1,000. But if you do this, right, the stellar mass density profile that we measure for this galaxy now in a central region is very comparable to local ellipticals. And what we are missing is, of course, several orders of mass in the outside. And so you can ask the question, well, if I take this star formation distribution and integrate this up, where does this galaxy end up? And you can see that it very naturally evolves onto the quiescent sequence and a quiescent size mass relation, basically forming these compact quiescent galaxies we observe at redshift of 2. And so with this, we also do this on the population side now. I just want to have 1 second. Okay, good. So then I will just say that there's, of course, a lot of new telescopes coming online. My retirement age is below the scale, which is nice, but there is basically a lot of new excitement coming on. For us at Cambridge, we're particularly excited about VLT moons, which allows us to start probing the cosmic web at redshifts of 2 and relate this to the galaxy population. And I think I will stop here. So thank you very much.